Today we're on chapter 2, okay, and it's looking at Newton's laws and free body diagrams, okay. This week we're going to cover free body diagrams, sort of, the idea behind them, how to do them for dynamics, because it's a little bit different from the way you do them in statics, okay. And then next week we're going to practice applying what we've learnt this week to some problems, okay. So it's sort of a two-part type lecture. This is the first part on Newton's laws and free body diagrams. Okay. Now if I can find the... Right. Okay, so we're going to cover Newton's laws, Newton's first, second and third laws. And then we're going to talk about types of free body diagrams, how to draw them, the difference between particles and rigid bodies, the respective equations of motion, okay, how to draw a free body diagram, and then we're going to do a couple of examples using the visualizer in the boxes that are on pages 28 and 29 of your notes. So, this is Newton, probably the most important man in physics, and possibly all humanity for the time being. One of the most influential people in human history, okay? And he did he was a mathematician, a physicist, scientist, lots of other things, philosopher, okay? But one of his things that we're quite interested in is his book, okay, which is known short as Principia, okay? And basically he uses that to describe a variety of his theories, okay, including Newton's theory of gravitation and all that sort of stuff. But the things that we're interested in are his 3 laws of motion. Okay. Now, Newton's first law was actually started before Newton published his book by a chap called Galileo Galilei in the early 17th century. And he said that a body at rest remains at rest, and a body in motion continues to move at constant velocity in a straight line unless acted upon by an external force. Okay. Now, what was important with Galileo's theory, okay, is the second part of that. Obviously, if an object's at rest, it's not going to move unless we act on it with a force. But what he also realised is that if something is moving in a straight line at a constant velocity, it will continue to do so if you don't act upon it with an external force. Okay, that was an important discovery that he made. And Newton picked up on this. So like I said, if an object is travelling at a certain velocity, there is no force necessary to keep it travelling at that velocity. And Newton picked up on that and came up with his first law. Okay, a bit of plagiarism going on, but not too bad. And he said that every body perseveres in its state of rest or in uniform motion in a right line, so a straight line, okay, unless it is compelled to change that state by forces impressed upon it. Okay, what does that mean? Well, essentially, it means that it's a continuation of Galileo's theory that if you set something in motion, it will continue going in that motion. Okay, and if you leave it at rest, it will stay at rest. Okay, if you've got an iPhone, you put it to rest. Oh, that might go, but if another object at rest, that will probably stay at rest. Now, Newton's first law is only valid for what are known as inertial reference frame. Now, what do we mean by inertial reference frame? Essentially, an inertial reference frame is a frame that is not accelerating. Okay? Okay, it's not accelerating. Now, where can we find an inertial reference frame? How can we do that? Well, the thing is that there aren't any inertial reference frames. Okay? We are all accelerating at the moment. We've got gravity acting upon us, okay? The Earth is accelerating. It's got centripetal acceleration around the Sun, okay? The Sun's got its own acceleration, its centripetal acceleration around the galaxy, etc., and so on and so on and so on. And as an example of that, imagine I'm on my bike perhaps, or I'm in a car, okay, and I'm accelerating. And you're observing me, and you can see that I am accelerating, okay? And you ask me, do you feel any acceleration? And I say, yes, I can feel the push at the back, in my back, okay? Now, if you look at it from the other perspective, look at me, I'm looking at you guys, and from my perspective, you're accelerating towards me. And I say, do you feel the push in your back? You know, the acceleration force. And of course, you feel nothing. So the inertial reference frame is only working when you're looking at me, but not when I'm looking at you. Okay? And so another example is, say you're on a plane and it's accelerating down the runway. Well, just before it starts accelerating, you put something on the floor. The plane starts accelerating, and of course that thing that was on the floor that was at rest heads to the back of the plane. Okay? And so that object that was at rest is now moving. And of course, from your perspective, that defies the first law. Okay? But it's all to do with these inertial reference frames, okay, which is a frame of reference that is not accelerating. Now, because such a situation doesn't exist, okay, how can we believe Newton's first law? Well, we do believe Newton's first law, okay. It cannot be proven because there's no reference frame, okay, but we believe in it because in any experiment that's been done, it's consistent with the results of that experiment, within the uncertainties of your measurements, okay. So that's Newton's first law. Now, Newton's second law, okay, let's think of a hypothetical situation. We've got a spring, okay. Now, x1 represents the spring's relaxed length, okay. So a spring at rest, okay. You pull on the spring, okay. If you extend the spring, the spring is going to try and return to its relaxed length. So it's going to be applying a force at the end of that spring to pull it back to the original position, okay. Now, say you take a mass of a certain mass, m1, okay, so this is the relaxed length of the spring, x2 produces a pull. You put a mass m1 on the end of that spring, okay, and you let it go. And that mass will then accelerate with a certain velocity, a1, back until the spring is at its relaxed length, okay. You then detach mass 1 and you put mass 2 on, okay. And again, mass 2 being different from mass 1, again, you let go, and that will produce an acceleration a2. Okay. Now, from that, there is an empirical proof that the mass times the acceleration for both of those things are equal to each other, because the spring hasn't changed. The spring is exactly the same. Okay. But you put two different masses on, you get two different accelerations, and you can show that those masses times by those accelerations will be equal to each other. And so you can say that m1 a1 equals m2 a2, okay? And this forms the basis of Newton's second law, okay? And this product ma is called a force. And Newton stated that the force action on a body gives it an acceleration which is in direction of the force and has a magnitude given by ma, okay? M being the mass and a being the vector of acceleration. And so mathematically, F equals ma. Now, you've probably all heard of that before. This is where it comes from, and we use it all the time in dynamics, okay? You shouldn't have to remember it. You'll use it so frequently that you'll have no problem remembering it. Now, can Newton's law be proven? Well, the answer to that is no. Again, Newton's second law requires an inertial reference frame, a reference frame that has no acceleration. Okay, do we believe in it? Well, yes, we do, okay? Why do we believe in it? Because it is consistent with the uncertainties of the measurements of any experiment that you do to try to prove it, okay? So we take it as a given. Now, F equals ma, a being the acceleration. Well, what happens if you're dealing with something that's under the acceleration of gravity, okay? Well, that's quite easy. You essentially replace a with g, okay? G being 9.81 meters per second squared, okay? And so your force of gravity is, and it can be mg, which is always directed downwards, okay? We're dealing here with vector quantities, okay? So I've written g, and that's F equals mg, positive quantities, but g is always in the minus j or minus k direction, downwards, okay? And of course, the units for force, obviously mass is kilograms, acceleration is meters per second squared. Okay, so you could write force is kilograms meters per second squared, but what we write is we say Newton in honour of the great man. So that's Newton's second law. Newton's third law. Okay, Newton's third law says if one object exerts a force on another, the other exerts the same in opposite direction on the one. Okay? I'll read that again. If one object exerts a force on another, the other exerts the same in opposite direction on the one. Now, this can be usefully summarized as action equals minus reaction. Okay? And the minus sign indicates that it opposes. Okay? So you have an object, there's me, I'm standing on the ground, I'm exerting a gravitational force on the floor, okay, and the floor is exerting a gravitational force upon me that is equal to in magnitude but opposite in direction. Okay? That force is upwards. I hold this in my hand. Okay? It's not moving, but it's exerting a gravitational force on my hand, and I'm exerting a force that's equal to that gravitational force, but opposite in direction on the remote control. Okay. And so the force of Ben Drew, okay, is equal to minus the mass of this times g. Okay. Now I've got an example to help illustrate this. Okay. We've got a force being applied at two masses that are in contact with each other. Okay, M1 and M2. And we can take Newton's second law quite simply and to find out the acceleration of this system as a whole. Okay, so you group M1 and M2 together as one lump. Okay, you've got a force being applied to it. You know the mass, M1 plus M2. You can find the acceleration. M1, let's say, is 5 kilograms. M2, let's say, is 15. And the force, let's say, is 20 newtons. Okay, plug that into Newton's second law. We can find the acceleration is 1 meters per second squared for the whole system as a whole. Okay. But what about the forces between M1 and M2? We know the acceleration, we know that force that's being applied. Let's look at block 2 on its own. So we've got block 2. And so we're taking out everything else except for the stuff that's acting around M2. Okay? And the only thing that's acting on M2 is the force from M1. Okay? The block M1 is being applied applying a force to M2, okay? And we call that force F12, okay? So the force that 1 is applying to 2. Now, for M2, Newton's second law states that obviously the sum of all the forces equals mass times acceleration, okay? So the sum of all the forces on this block is F12. That equals mass times acceleration. We know the acceleration now. We also know the mass. And so we can work out what F12 is, and it comes out to be 15 newtons. What about if we look at M1 on its own? Well, M1 on its own looks like that. So you've got two forces being applied. You've got a force, the original force that was being applied, and you have a force that's being applied in opposite direction, but equal in magnitude, F21. Okay? But let's assume that we don't know what F21 is at the moment. Okay? We know F12, that's 15 newtons. Let's assume that we want to work out what F21 is. Okay, so again, you apply Newton's second law. And this time, the sum of all the forces, well, you've got F plus F21, okay, equals M1 times A. Okay, so F21 equals M1 times A minus F. Okay, and so you've got 5 minus 20, which equals minus 15. And so you can see that F21 and F12 are equal in magnitude, but opposite in direction. Okay. Now, is this a proof of Newton's third law? No, it isn't. Okay. In Newton's third law, can it be proven? No, it can't. Do we believe in it? Yes, we do. Why do we believe in it? Because within the uncertainties of any measurements that have been taken, it is consistent with our results. So those are Newton's laws, Newton's 3 laws of motion, and we use them all the time in dynamics. Okay, they have rotational equivalents, and we'll cover them later on, except for one of which we'll cover today. Okay, but they are fundamental to what we do in this course. Okay, they form the basis of a lot of the work that we do. Okay, so free body diagrams. Now, when we model a system, or when we're trying to analyze a system, we can generally classify our system or an object, or whatever we're trying to do, into 2 of these idealizations, okay? The first one is known as a particle, okay? Now, a particle has a mass, but we assume that it has no shape or size, okay? And so, it is one particle, one point in three-dimensional space, okay? And one of the advantages of a particle is that you can't rotate a particle. Obviously, if it's got no size or shape, it doesn't matter whether the particle is right way up or upside down. It has no shape. It doesn't matter, okay? And so you can't apply moments to the particle. And we use a rectangular coordinate system with our particles. We tend to use the right-handed coordinate system that we covered last week, okay? There are other coordinate systems that we use, but we will choose to use the right-handed coordinate system. It generally works quite well for us. The second type of object is what's known as a rigid body. Now, this has a mass, like a particle, but it also has a shape and a size, okay? And that means that you can apply moments to such a particle, to such an object, okay? And those forces aren't necessarily directed at the object's center, the mass center, G, okay? We call that G. And again, we can apply a rectangular coordinate system. Again, we tend to use the right-handed one. But in some situations, you might want to choose to use a curvilinear coordinate system that deals with things like rotation and angles and stuff like that. And we'll cover that in more detail later. So there are the two types. We've got a particle and a rigid body. Well, what are the equations of motions for a particle? Okay, so when you've got a particle, you've got a system of forces acting on the particle. Newton's second law may be written in the form of the sum of all the forces equals the mass times acceleration. Okay, so I've got a particle. Let's assume for the time being that this is a particle, and you've got a load of forces being applied to it. Okay, the sum of all those forces equals its mass times acceleration. Obviously, if it's not moving, acceleration is 0, and you have the sum of all the forces equal to 0. That's what you covered last semester with statics, okay? Sum of all the forces is 0. Here we're dealing with dynamics. We're not scared about the fact that it moves, okay? Mass times acceleration, and that will give us information about the acceleration of that particle. Now, a free body diagram, we use these as a sketch of the object free from all its surroundings, okay? So the free body diagram of this sitting on the table would be a block, okay, with a force being applied by the table to the block, and obviously the mass force of that thing being applied to the table. And obviously in this case, the sum of all the forces equals 0 because it's not moving, okay? But if something is moving, then obviously the sum of all the forces equals that mass times acceleration. Now what we do with free body diagrams is we tend to match them up with a corresponding kinetic diagram. Okay, so you've got your free body diagram, you've got the two forces. Your kinetic diagram is essentially the block and the direction that we think it's going to accelerate, ma. Now we'll go through an example of that in a second. Okay, so that's the equations of motions for a particle. And so with the free body diagram and the kinetic diagram, because the sum of all the forces, which is our free body diagram, equals ma, which is our kinetic diagram, obviously those diagrams equal each other. Okay, and it helps you visualize what you're trying to solve. So it's quite important that you're good at drawing free body diagrams. You'll be using them all the time. Okay. What about for a rigid body? Okay. Well, we've got the same equation for a rigid body. Okay, the sum of all the forces equals the mass times its acceleration. Now, this time, because we're dealing with an object that has size or shape, that acceleration is going to be acting on the mass center, which is why we called it AG. Now, in terms of rotation, as we said, we can apply moments. Well, we have the sum of all the moments being applied to that equals the moment of inertia, I, okay, times by alpha, which is the rotational acceleration of that object. So say you had a pulley, okay, and you've got a force being applied on the pulley by a mass, say, okay, and obviously when you release that mass, it turns the pulley, and so that mass has to, obviously it's accelerating due to its own weight, okay, but it's also accelerating the pulley, and we need to account for that in our free body diagrams, okay, so you have these two equations for rigid bodies. You've got the force equals mass times acceleration, and you've got moments equals the moment of inertia times by the angular acceleration, alpha. Okay. Now obviously if an object isn't rotating, then alpha is 0, and you just have the sum of all the moments equaling naught. Okay, which is what you had in statics. I don't know whether you ever did a problem with a crane or something. Obviously we don't want the crane to fall over, so the sum of all the moments acting on that crane is 0. But because we're dealing with dynamics, there's something that's going to be moving, and so we have mass times acceleration. And again, we'll go through an example of this. Now, friction. I was unsure whether you've all covered friction force before, but I thought, well, since we're going through it, I may as well do so. Now, when you've got an object being applied, a force downwards, say, on a table, on a horizontal surface, okay, we know full well that it's applying a force downwards due to gravity. And we know also from Newton's third law that there's a force being applied in the upwards direction on that object. Okay? Now, say we try and move the object, okay, well, we can feel a resistance force. And that resistance force is due to friction between the object and the surface along which it's running. And the friction force is defined, we know Fg, okay, that's mass times acceleration due to gravity, okay, and we know that the opposite is equal and opposite to that. We call it what's known as the normal force, okay, and in this case that's going to be minus mg, okay, because it's in the opposite direction. Now obviously if the object was sliding along a slope, okay, you've got gravity which is always pointing downwards, but the normal force is called normal because it's perpendicular to the surface along which it's running. So we've got an object sliding down a slope, okay? Gravity is this direction. The normal force is going to be perpendicular to the slope, okay? So in that case, you wouldn't have m minus mg. You'd have mg sine or mg cos at a certain angle. But we deal with the normal force, and the friction force is known as F, friction, force of friction or friction force, okay? Is this value mu, which is the coefficient of friction, times by n. Now the little subscript k indicates that we're dealing with what's known as kinetic friction, because friction can be quite complicated, okay? You tend to have two types of friction, kinetic and static friction. Now the static friction is the force required, well it's a frictional force to actually get the thing moving from rest, okay? And often with objects where there's friction being applied, that force is greater than the force necessary to keep it moving once it is moving, okay? Which is why we've got static friction and kinetic friction. Generally, if we don't specify which one it is, you can assume we're dealing with kinetic friction, okay? We're not, we'll give you those forces if we'll give you those coefficients if we need you to work them out. So we now know the equations of motions for a particle. We know the equations of motions for a rigid body. We've got frictional force, okay? And so we can start to think about how do we draw a free body diagram. And essentially there's a bunch of steps you need to go through. Step 1 is you need to select a coordinate system. Now, like I said, most of the time we choose to have a right-handed coordinate system, okay? So we've got x and y and k, or z, okay, which in a right-handed coordinate system, if you were to draw x and y, you'd have x along the x-axis, y along the y-axis, which we all know, and k, due to our right-handed coordinate system, x, y, z, coming out of the page, okay? Right-handed coordinate system, x and y, z. The next step, you need to work out what you want to draw the free body diagram of, okay? So say you've got a crate or a truck or a car or whatever, that is your object, okay? You isolate it from all its surroundings and you can draw its outline shape. If you're dealing with a particle, you can just draw a block. You don't need to worry about its outside shape, okay? You then draw your block and you apply all the forces that are being applied to that. So we've got gravity, we've got normal forces, we've got forces of pulling, forces of pushing, frictional forces, spring forces, all these forces, you generally apply all those things to that object, okay? And if you're dealing with a rigid body, you need to apply those forces at the points at which they're being applied, including the dimensions between that point and the point about which it's going to rotate, be that the mass centre or another arbitrary point that you have, okay? So say you're dealing with a car, okay? I think you're doing engineering design, so you probably are trying to work out at the moment the forces acting on on the car, on the front axle, okay? Well, what you could choose to do is you could look at all the forces being applied, okay? You've got your normal forces being applied at the wheels, you've got your mass force being applied around the centre of mass of the car, okay? And you could take moments about the centre of mass of the car. Or, alternatively, you can take moments about the contact point of that front wheel. So when it's braking, you know how much force is being applied to the front wheel, and you know how much force is being applied to the back wheel. Again, the same when it's accelerating. But you have to pick a point about which you apply the moments, okay? And that point can be anywhere, but it's often useful to apply that point where there is a force being applied, because then you don't need to include that force in your equation. We'll go through that in a second. Now, the direction of force having an unknown magnitude, you can just assume that it's going in some direction, okay? What will happen is when you calculate the numbers to work out what this force could be, obviously if it's coming out negative, then obviously it's in the opposite direction to the one you assumed. Very simple, basic. So with our kinetic diagram, we've got your free body diagram with all the forces. Kinetic diagram, we've assumed that it's accelerating, say, to your right, okay? Now, if your acceleration figure comes out negative, then obviously it's actually accelerating in the opposite direction, okay? You just make the assumption. And the direction of acceleration of a mass centre, AG, okay, should be established and either identified on a kinetic diagram, or the other way that people do it is they don't bother with a kinetic diagram, but they specify A in your coordinate system. So that's the steps to go through a free body diagram. So what I want to do now is actually I want to run through examples, okay? And this first example is on page 28 of your notes. Fingers crossed. Here we are. So there's page 28. Here's our example. Let's zoom out a bit. Okay. And the example says a 50 kilogram crate rests on a horizontal plane for which the coefficient of friction is 0.3. Okay. The crate is subjected to a towing force of magnitude 400 newtons and moves to the right without tipping over. Draw the free body and kinetic diagrams of the crate. Okay, so I've got a little box there. And what we'll do is we'll follow the steps that we've done. Okay, I'm just going to fold this over. So you can see what I'm doing. Right, so the first step. Somebody tell me the first step. Select a coordinate system. Right, so I'm going to choose the right-handed coordinate system. There's my right-handed coordinate system. I call this X, I call this Y, and I call this Z. Okay, I could also call it, if I wanted to, you could do the same thing. This is perfectly adequate as well. You say I, J, and K. Okay? Now, for an object coming out of the page, you draw it like this. For an object going into the page, you do that. Okay? Whoops. Out of the page, into the page. Okay? Now, obviously, with both of these, you've got an object coming out of the page. So this is the one to choose for K or Z. Okay? So there's our coordinate system. We're dealing with a particle. Okay? We're not worried about whether it's rotating or something, so we can draw the block as a block. So there's our block. Okay? We've got its mass centre here. Okay? And we know that that's going to equal a kinetic diagram. So again, we can draw its mass centre there. Now what I'm going to do is I'm going to apply all the forces in red. Okay, so we know what the forces are. Okay. Now obviously we've got a gravitational force. So there's our gravitational force. Okay. We've got this pulling force, this P. Okay, so we need to apply that. But because we're dealing with a particle, you apply that to the mass centre. All the forces are being applied to that block at its centre. Okay? So we have a force here, P. Okay? And we know that that angle, okay, is 30 degrees. So we've got P here. It's a vector. mg is a vector, okay. We've also, because there's an equal and opposite force to the mass, we know that there's a normal force associated with that, okay, being applied by the surface. And so we'll call that N, okay. And we can make an assumption, well, the two vertical forces, they're going to cancel each other out. But there's a force going in that direction, and we know, so if it's moving in that direction, there must be a frictional force in the opposite direction, okay. But because friction only acts normal to the sliding surface, the frictional force is in this direction. Okay, so that's going to be F, F, and you draw an arrow over the top. So if we go around that mass, those must be all the forces that are being applied on that block. Okay? We've got our block at the top there. Okay? We've got P being applied. The block has a mass, so there's a force downwards. Obviously that's being reacted by the surface, so there's a force upwards. And there's a friction force between the block and the surface, okay? There's no wheels or anything like that. It's not free of friction. And so those are the four forces being applied on our object, okay? Now, let's assume, for the time being, that the mass is moving to the right. And so you apply a force, well, a thing here, and that's going to be your kinetic diagram, MA. So there you go. You've got your free body diagram and your kinetic diagram. And so we know from the equations of motion that the sum of all those forces are going to equal the mass times acceleration. Okay. So that's with a particle. What about with a rigid body? Okay. Well, if you turn to page 29, okay, has everybody got that? Yell if you've not got it. Page 29, okay. We've got a similar thing. This example also involves a 50 kilogram crate. A force P is applied to the crate as shown in figure 2.6. The coefficient of kinetic friction this time is 0.2. Okay? So we've got a similar thing. We've got a crate and we've got force being applied, P. Okay? Now P is being applied at 0.8 meters above the ground. Because we've not been told anything about where the mass centre is, we'll assume the mass centre is in the middle, okay? And so we define a coordinate system. That's the first step. So I'll do the same thing again. I'll use the I, J, K one. I, J, and K. Hopefully last week you will have worked out the method that you want to use for your coordinate systems in terms of your notation. The key is to choose a system and be consistent about it, okay? Don't change systems halfway through, but you must always, I noticed some of you when you were working on the tutorial sheet problems, you were doing your decomposed form, the answer was fine, but you weren't saying that I, J and K were vectors. You must do so, okay? If you give me an answer in an exam and you've got we wanted a vector in decomposed form, you wrote I, J and K, but there weren't arrows over the top or hats on top or lines underneath, then you lose some marks because you're not signifying that those are vectors. It's very important that you do that. And that gets more and more important the further on you run. Because next semester, or next year, in fact, you'll be doing dynamics level 2, okay? Do even more with vectors, okay? In DMV, we start to deal with stuff in 3 dimensions, okay? So it's very important that you know you're dealing with vectors, okay? So we've got our vectors here, our unit vectors. We draw a block, okay? Obviously a crate this time, we know it's square, so we'll just draw a square. That's quite simple. Okay, there's its mass centre. And we know that that's going to equal a kinetic diagram as well. Mass centre. Okay, so again, I'm going to take a red pen to draw the forces. And we've got gravity. That's fine. Easy peasy. I'll draw that there. That's going to be mg. Okay? we've got our force P acting at this point here. So I'll draw that in. Okay, that's P. And we know that the dimensions, okay, well, we know that this dimension here, that's 0.5, okay, between there and there. And so the dimension between here, because that's 0.8, we know that that is 0.3, okay? So there's some dimensions. Now, at this point, we need to make an assumption about what we're trying to analyse, okay? And the assumption that I'm going to make is that I'm going to assume that our force P is not going to topple the crate. You can imagine if you're pushing a crate along, okay, along a flat floor, okay, if you apply the force high enough up, it could catch at the bottom and topple over, okay? I'm going to make the assumption that it's not, it's sliding, okay? Now, for it to slide and not topple, obviously that force P is applying a moment about the mass centre, isn't it? Okay, the moment being P times by the radius, or the distance, 0.3 metres, okay? And so that moment that's being applied about the mass centre needs to be opposed by a force that's opposing that, okay? And so, although we've got a normal reaction force due to gravity, that's not being applied to the mass centre. It's being applied at some point, okay, along here, so that it's opposing that force, because we're making the assumption that it's not toppling, okay? So I'm going to draw my normal force. Let's draw my normal force here. And what I don't know about my normal force is I don't know this distance. So I'm going to just call that x. Okay, I don't know that distance. And what we can do is when we work out the problem, if x is between 0 and 0.5 metres, because obviously we know that dimension there, that's 0.5. Okay, if x is less than 0.5 metres, then we know that we were right in assuming that the box doesn't topple. Okay. Now the last thing that we need to apply is the friction force. Okay, and so here's our n. The friction force is going to act in this direction. Draw it in red. And there's our friction force. FF. And obviously, that's going to equal our kinetic diagram, MAG. So there we go. Free body diagram and the kinetic diagram of a rigid body. Right. Has everybody got that? So, in summary, Newton's first law, every body perseveres in its direction of motion, if at constant velocity, unless it's compelled to change by the state of forces, by forces impressed upon it. Obviously there's a typo here. That's what I mean to write. Okay. Newton's second law, force equals mass times acceleration, okay? So the sum of all the forces equals mass times acceleration. And obviously, dealing with gravity, the Fg, or the force due to gravity, is going to be m times the acceleration of gravity, 9.81 meters per second squared. We assume, I don't know whether at school you assume 10 or 9.8. Here we make the assumption that we're not dealing with 9.81, okay? As the force of gravity, or the acceleration of gravity. Newton's third law, action equals minus reaction, where the minus sign indicates that it opposes the direction of the original action. Okay, a particle has a mass, but no size or shape. Okay, we don't apply any moments to particles. And if you're making a decision between whether something is a particle or is a rigid body, think about, what you're analysing. Okay, does it matter if it's tumbling? Okay, how big is it compared to the general scheme of things? Okay, if you're dealing with the forces that are acting on a car that's accelerating across the, the desert or whatever, then you can just assume that you're dealing with a point mass. If you're trying to work out the moments being applied at the wheels and the forces being applied at the wheels, and whether, obviously with Bloodhound, the land speed record car, one of the things they wanted to make sure that is it didn't take off, and it also didn't dig a big hole. Okay? They needed to make sure that the moments were such that the thing stayed on the ground, okay, but wasn't so forced in the ground that it would make the fastest hole in the world. Rigid body, so that's what you deal with a rigid body, okay? Mass and a size and a shape, okay? For particles, you apply Newton's second law, the sum of all the forces equals mass times acceleration. And for a rigid body, you have that one, and you also have the rotational one. The sum of all the moments equals I times alpha, alpha being the angular acceleration. And we'll go into more details with this next week when we start applying numbers to these sort of equations, okay? Friction, you've got your static and kinetic friction, mu s and mu k, okay? Mu s is always greater than mu k. And the force of friction is mu times the normal force acting on that body. And the main rules of drawing a free body diagram, you've got coordinate system, isolate the body, draw the forces being applied to the object. If the object's a rigid body, you've got moments, and you need to work out which direction A is going. Now, before you all pack up, I've got a little thing for you. Okay, I have with me my bicycle. You're probably wondering why I brought it with me, okay? Okay, I've got my bicycle. And I want you to tell me, if I apply a force to the pedal, this pedal here, in that direction, which way is the bike going to move? If I apply a force to the pedal, I'll just put it up on the screen a second. If I apply a force to the pedal, okay, in that direction, which way is the bicycle going to move? Sorry? No, I'm not riding it. I'm just going to push a force on that pedal. Which way is it going to go? It's going to go that way. Okay? That's what you'll think. Think about the free body diagram. Okay? I've got an object, and I'm applying a force that direction. Which direction is it going to go? It's going to go that direction, isn't it? I'll try again without holding the saddle. Okay? So I'm applying a force in this direction. Okay. Yep. It goes in that direction. And that's because if you think about it, you've got a force that's being applied to the pedal in that direction. Okay? Doesn't matter what's going on with the change. If you treat the thing as a particle, it's going in that direction. It's a little more complicated than that because we draw our free body diagram. Let's assume that we're doing the whole thing. You've got a force being applied here, and you're right that there is going to be a force transmitted through the chain to give you a force being applied at the back wheel. But generally, you have to have some really extreme gearing for P to be greater than F. Okay? And so, obviously, in the vertical direction, you've got the mass and you've got the normal reaction forces. And essentially, if you resolve in this direction, you've got P minus F equals the mass times the acceleration of the bike. And generally, F is greater than P, and so the bike moves in that direction. Although, intuitively, you think, well, because of the chain, it's got to move in that direction. That's what we do when we ride a bike. But that's not true. And if you've got P such that P is greater than F, and for that you need some really, really big gearing, or F needs to be below the ground, okay? The bike will move forwards, but because of the gearing, your pedal will still always move backwards, okay? And I've tried this with a mountain bike where the gearing is such that you're pedaling faster than the wheels are going around, so you have got some, and the bike still goes backwards, okay? It's not intuitive, but this is the way Newton's laws are being applied to objects, okay? The bike moves backwards. It's not intuitive. Right, thank you very much. See you next week.